All right, one of today's lessons is on mass, weight, and the force of gravity. Um, if you're thinking about how to organize your note here, it's going to be mass on the left and weight on the right. They are different quantities. Mass is the amount of matter that an object has. It's measured in kilograms. Can also be defined as an object's inertia. Weight, on the other hand, is the force of gravity. We use it incorrectly often, and since it's a force, it's measured in newtons. So weight is properly measured in newtons, mass in kilograms. One of the most common mistakes in this chapter is a question on a test or any sort of assessment will say something to the effect of find the weight of a particular object, right? And people think in the back of our minds, we think that weight has got to be kilograms or pounds, but weight is properly measured in newtons. So weight can be calculated by the formula Fg equals mass times little g. Now, lowercase g on Earth is familiar to us, 9.81. Usually we have it measured in meters per second squared, but it can also be measured in newtons per kilogram. On the moon, it's less, 1.6 newtons per kilogram. And the planet that, off the top of my head, the planet with the most gravity in our solar system is Jupiter with 25.8 newtons per kilogram. That would be at the surface of all these planets. Not that Jupiter has a solid surface, but if it did, that's what the gravitational field strength would be. I don't know what else to say about that little g. It's also sometimes termed gravitational field strength. You see its units as newtons per kilogram, but it can be measured in meters per second squared as well, right? It can also be defined as the acceleration due to gravity. Over on the left here, there's two ways to define mass. One way is what it says right at the start, the amount of matter packed into an object, but you can also think of it as an object's inertia, where it's the ratio or the fraction of F net over A. That comes from Newton's second law. We've already covered that. Or you can think of it as the gravitational mass, which is just force of gravity Fg divided by g. That's just taking this formula over here on the right and rearranging it and solving it for mass. So there's a couple of ways to calculate mass. Again, if I'm talking too fast here, as I am on my third cup of coffee, just go right ahead and pause the video anytime you feel you need to. So that's pretty much the note on weight and force of gravity versus mass and inertia. But what types of problems are we going to have to solve with it? So determine the weight of a 98 kilogram person on Earth to start with, and then we'll calculate the moon as well. So on Earth, weight is force of gravity. That's one of the main things to get out of this problem is just when it says find the weight, it's asking for the force of gravity. So it's mass times g, which in this case will be 98 kilograms times 9.81 newtons per kilogram. The kilograms cancel out and you're left with newtons. If you put that in as meters per second squared, I wouldn't mark that wrong either. So rounded to two digits, I get 960 newtons. So if my mass is 98 kilograms, then my weight on Earth is 960 newtons. Now, if I go to the moon, my mass doesn't change. I'm still 98 kilograms, but my weight, what I feel, the force of gravity, it does change. You go 98 kilograms, because wherever I go in the universe, that's going to be the same, times 1.6 newtons per kilogram. And I'm going to find I weigh a lot less. It's about 1/6-ish. And again, rounding to two digits, I got about 160 newtons here. I got more digits on my calculator there, but I rounded my answer. So that's how much I weigh on the moon. That's how much I weigh on Earth. It's measured in newtons. So on a test, if you're asked for weight, make sure your answer is in newtons, not kilograms, not pounds. We're never going to use pounds in this chapter, as a matter of fact. Kilograms for mass, newtons per weight. Jupiter. All right. So my weight on Jupiter, well, it's going to be more. My mass is still 98 kilograms again, but Jupiter, I got to go back a slide, 25.8. Usually I round it to 26. Is 25.8 newtons per kilogram for gravitational field strength. You punch that into your calculator real quick, 98 times 25.8, and rounded to two digits, I got 2,500 newtons of weight. So I feel heavier. I feel more gravity on Jupiter because Jupiter's bigger. So hopefully that seems pretty easy. But what can I do to trick you? Well, here's a way I could trick you. Give you the mass in grams. Force of gravity equals mass times g. Unless otherwise stated, I'm assuming this is on Earth. I don't think it makes sense to find the force of gravity on a toy car on the moon or Jupiter or any other planet for that matter. So you got to just know that that's 1.5 kilograms times 9.81 newtons per kilogram. That'll be 14 something. If I round it to three digits here for the 9.81, see the 1500, technically you could say it has four digits, even though I wrote it with two digits here. So I'm going to round my answer to three digits, which is 14.7 newtons of weight or force of gravity. You know, that term right there could be weight. Next one, find the force of gravity, or it says the force of gravity on a rock is 560 newtons. What is this weight? What is this mass? I like this. I've used this on a test before just to see who really, really didn't know what they're doing. Well, the answer to A is 560 newtons. Just yet another test of knowing that force of gravity is weight. And then we can find its mass. Mass equals force of gravity divided by g. I'm assuming this is on Earth. This is 560 newtons divided by 9.81 newtons per kilogram. On Earth, we go 560 divided by 9.81. It gives me 57 kilograms. 57.1 if I want to use three digits. 57.1, I guess, is a better answer there. The last little bit to go over here is sometimes even on Earth, you can feel heavier, you can feel lighter, depending on your acceleration. Like how you feel really light when you go over the hill on a roller coaster. You feel really heavy when you're at the bottom of that roller coaster when you're accelerating back up. Basically, anytime you're accelerating up, you're going to feel heavy. Anytime you're getting close to free falling down, you're going to feel lighter. So weight, this is just reviewing force of gravity on the object. Apparent weight is the weight that you feel due to a combination of gravity and also your accelerating frame of reference. So on an elevator, if your acceleration is 0, then you have Fg equals mg, which is just your normal weight. The elevator is a good example because it only accelerates up and down. I don't have to think about any sort of twists and turns or horizontal motion. So I'm going to keep my questions for the most part to the elevator. Sometimes I'll do an airplane coming out of a dive. You'll see that in a minute. However, if the acceleration is not 0, then we use this instead. And I usually write it like this. F apparent equals m times g plus a, just to remind myself that it's for apparent weight. Now, if you're using your formula sheet at home, this isn't on your formula sheet, so you can add it to your formula sheet if you want. But you know, as long as we're working from home, your assessments are going to be open book anyway, so you can always come back to this note as you're doing this. So do you need to add it to your formula sheet? Totally up to you. If we get back on May 4th like we're supposed to, then you may need it on your formula sheet. But for now, Put it on your formula sheet. Don't put it on your formula sheet. It's totally up to you. Um, the biggest, ugliest problems that you'll have to solve would be one like this. So elevator is going to be doing a bunch of different things. So guy in an elevator, standing on a scale. What will the scale read when the elevator is at rest? When the elevator is moving at a constant velocity? When the elevator is accelerating up? When the elevator is accelerating down? So when it's at rest, no acceleration, we can just say, okay, we're just calculating his weight or his apparent weight here. So no acceleration is just going to be the normal formula, 75 kilograms times 9.81 newtons per kilogram. So I go 75, 9.81, and I got, I'm going to round it to 2 digits here, which is going to be 740 newtons. Calculator actually gave me 735.75. Now, part B is a trick. On a test, I might mark this out of 3, so you have to show the formula, and you have to sub into the formula. You got to give me the answer, that sort of thing. Part B would actually be out of just 1. And that's because I'm hoping everyone will see that moving at a constant velocity, even though it's 2 meters per second, still means no acceleration. So you get the same weight as before. It's normal 740 newtons. So this is like once the elevator is up to speed, if it's a decently constructed elevator, you just feel your normal weight as you're traveling at a constant speed, up or down. Doesn't matter. You only feel different when the elevator accelerates, when it's changing its velocity. So in the first one, it accelerates up. So when the elevator first starts going up, my sensation, and it should be yours too, is that you feel heavier. So if I do this apparent weight calculation, I'm expecting to get a value greater than 740 newtons. So let's see what I get. So we use the apparent weight formula now because we are accelerating, and that's going to be m times g plus a. So that's 75 kilograms, 9.81 newtons per kilogram, plus 1 meter per second squared. If you're real good at math, it might look awkward to be adding newtons per kilogram and meters per second squared. But I've explained before that they're actually the same unit, just expressed a little differently. So if I type that into my calculator, if you want to do it all in one step, make sure you put brackets in there, 75 times bracket 9.81 plus 1. Close up your bracket, and you should get a heavier than 740 weight. Feel free to pause the video. To 2 digits, I get 810 newtons. 810 newtons. When the elevator is accelerating down, and we know it's down because of that negative acceleration, just apply the same formula. F apparent is equal to mass times g plus a, which is equal to 75 kilograms, bracket 9.81 newtons per kilogram, minus 1.0 meter per second squared. Now I'm thinking we should feel lighter. This is when the elevator accelerates down. So let's type that in. Make sure you put the bracket, 75 times bracket 9.81 minus 1 this time, and I got 660 rounded to 2 digits, 660 newtons, and that is rounded off. My calculator had more digits on it, but I rounded my answer. So you feel lighter when you're accelerating down in an elevator, heavier when you're accelerating up in an elevator, and if it's going at a constant velocity or at rest, you feel just your normal weight. One more before we stop here. And I don't know if I'll be able to get you that video link or not. The acceleration of a plane as it pulls out of a dive is 67.8 meters per second squared. If the pilot has this mass, determine the apparent weight of the pilot. And how many G's does that pilot feel? Anyways, let's do A first, and then we'll do this whole G-force idea. So A, Determine the apparent weight. Well, obviously, we're going to use this version of the formula. Then mass times G plus A is equal to 85 kilograms. And let's just think about that. We're going to be multiplying. We are accelerating up, so it's 9.81 newtons per kilogram plus 67.8 meters per second squared. Again, it's okay to add those two things together. And I'm going to go 85 times 9.81 plus 67.8 bracket equals. And I'm going to round that to two digits again, I think. Yes, for the 85 kilograms, it's going to be 6,600 newtons of apparent weight. Now, as far as the G force goes, 1G would be like your normal weight. Right? 1G is normal weight. So the normal weight is just mass, 85 kilograms, times 9.81. I'm just going to do that real quick for you. 85, 9.81. So your normal weight is 830, just to round it off. And that's supposed to be an N for newtons. All right. But this is your apparent weight. So the ratio, if you were feeling 830 newtons, then that's 1G. 830 divided by 830 is 1G. But your number of G forces, how many G's does the pilot? I'm going to go down to the bottom left here. Your G's is going to be equal to your apparent weight, 6,600 newtons, divided by your normal weight, 830 newtons. And that'll roughly give you how many G's. I know I rounded my answers there, 6,600, but this is going to give you a nice approximation. And I got approximately 8 G's. My calculator actually gave 7.95, but it's about 8 G's of force that you feel, which is dangerous. I think the maximum a roller coaster is supposed to, like by law, be able to expose you to is around 4 or 5 G's. At 8, it gets to be actually kind of dangerous. I don't know where I got these numbers from, if they're legit or not. The roller coaster physics video, I'm supposed to be limiting you to about 3 hours of physics work per week. And if I throw in this, even though it's a 25-minute just for fun video, I'm not going to post the link just in case any of you are whiners and say we had to watch that video. And that added to the 3 hours. So I'm not even going to do that. It's called Roller Coaster Physics. If you look it up on YouTube, good for you. I've got one more short lesson to go after this for the week, and then that's it. You just do some practice questions, and away we go. All right, that's it for now, guys.